start. Okay, then from last day, at the end, what we have discussed, actually, we started our discussion about the transistor. And for the transistor configurations, we have two types of transistors, that is N-type and P-type. Then for that, we identified then to turn on transistor, what are the conditions. We had forward bias base emitter junction and reverse bias base collector junction. And these are the various curves we have discussed. This VBE and IB is similar to diode curve. Okay. The other one, IB versus IC. Then here we have a relationship. This IC equals beta times IB. Beta means the AC current gate. And we have another name for this beta is HFE. In addition to that, we have a different graph, that is VBE and IC. And there we can show three modes of the transistor. Cutoff mode within the cutoff mode, transistor is not working. And in the linear region, transistor is working as a linear device. Then the main application there is that we can use transistor as an amplifier. Okay. The third region is saturate region. We can use this cutoff and saturate region for switching action. Then in one end, we can use transistor is switch off. The other end is transistor is fully on. Here also the active region is, we can consider as on region, but it's not fully on. During this region, the transistor is working as a linear device. But although we are saying it's on, it's proportional to VB, IB and IC. We have this relationship, valid relationship here. But when it comes to the saturate region, this relationship is not valid. IC equals beta IB is not valid. Then you can increase IB to a greater value, but IC is not increasing with that. Okay. Okay, then we have this one, the BCE IC one. Here also we can mark these three regions there. And after that, we discuss about transistor applications, transistor as a switch. The important thing here we have to remember is VCE. This VCE here, this one, when transistor is saturated region, this VCE we are taking as much as close as 0.2 volts. This one. Okay. But then if you want, you can consider this as 0 volts, depending on situation. But anyhow, that is the situation. And we had this one, then we can turn on this one, and we apply certain voltage to this V in. Then when we apply this V in voltage, we can turn on this transistor by forward biasing this base emitter junction. Then transistor will be turned on and it will be driven to saturate region. Then during the saturate region, VC is 0.2 volts, then VRL, this resistor voltage is almost close to VCC. The meaning is VC is 0. Did you understand that one? Okay, we had a example also. Okay, the simple meaning here is that when V in is 0 volts, here this V in is 0. Because of that V in is 0, this VBE, this is also 0. Okay, then transistor is not turned on. This is off. We can consider this transistor is off. Because of that, is IC is not is 0. Because IB is 0. When V in is 0, this junction is not forward bias. Because of that, there is no current going to this IB. Then IB is 0. Because of IB is 0, IC is 0. Then VB is 0. Then because of that, this current is 0. What happens here is this V out, this voltage drop across this RL is this VRL. This VRL is 0. If VRL 0 means this V out is equal to plus VCC. That means this is equal to VCE. Then VCE is equal to plus VCC. That is V out. Okay. Then the other side of that one, when V in is greater than 0, this may be certain voltage. Here we can see this VB is 0.7 volts. Because of this 0.7 volts, this IB is in greater value. Because of that, this IC is also there. Then this PCE, you can take this as 0.2 volts or as very much close to 0. Then if this is 0, this VRL, okay, then we can write equation VCC equals to VRL plus VCE. Am I correct? This VC is V out. This one. Then VCC is equal to VRL plus VCE. But anyway, that we are taking this VCC is 0 volts plus it's 0 volts. Then VCC is equal to VR. This one. But here The earlier time, here we have voltage drop 0, then VRL is 0, then VCE is equal to VCC. Then here we have high voltage. But here in this case, when Vin is in sufficient stage, Vin is greater than 0. 0 means it should be, actually it should be greater than at least 1 volts. This condition should be there. Then here we can maintain 0.7 volts. Because of that external path, we have high current. Then as a result, this current is going across the resistor. Then this VRL is generated. But anyway, that when we drive transistor into saturate region, because of that, the VC may be 0.2 also 0. Okay. Is it okay? Is it okay? Okay, then if it is okay, we can start from that point. Okay. I think you can see the screen. Here. This is our transistor. We have this 0 volts line. And here on the top, we have this power line, VCC. Here, have this one. And this resistor. Okay. And these are the only things that we have here. This is the input voltage. And we can take this one as V out. This is what we discussed. This is RB. And this is the resistor. Okay. But we have a lot of applications here. For example, if you want to turn on a, maybe assume that if you want to turn on LED, you know how to turn on LED. But to turn on LED, we don't need a transistor. But anyway, that if you want to turn on transistor with a lot of transistors, sorry, a lot of LEDs, how can we do that one? We can start from LED, then we can do it. For the other things, we can do it easily. You can understand these things easily. Then shall we try to do that one? Okay. Then here we can include an LED here. Then to balance this one, then we will put this resistor. This is LED. Okay. Then how can we do this one? Then this voltage we can take is plus 12 volts. Assuming that this voltage is plus 12 volts, then we can take this beta of this transistor as 100. And here we have this resistor and this LED. When we turn on this LED, the current we want to send through this one is this. Shall we take 20 milliampere? Okay. And when we turn on this LED and across the LED, what is the voltage drop here? We can take it as 2.2 volts. Okay. Then how do we turn on this one? You know that when V in is 0 volts, transistor is off, and then LED is off. Why? When V in is 0, there is no IB current. We cannot forward bias this base emitter junction. Because of that, there is no IC current. Then current is not going through the LED or resistor. Then LED is turned off. Okay. But then assume that when V in, we can take it as 5 volts. Now LED is 5 volts. Then we have to find from this how much of IB current we need. Assuming that the relationship is this IC equals to beta time IB, then we can find, because we know this IC is 20 milliampere and beta is 100, then we can find IB. This is 20 milliampere. This is 100. Okay. And it's 0.2 milliamperes or maybe 200 microamp. Okay. Then when we turn on this one, we know that here we have to maintain 0.7 volts. Okay. Then VBE should be 0.7 volts. At that time, what is VCE? You can take VCE as 0 volts. Okay. Then this B in is first 5 volts. Then you can calculate RB. How can we find RB? Here. This is IB. We have to find, we know IB, we know V in, we know this side is 0.7 volts. Then we can find RB. Sorry, RB. Because of that, we know VRB. VRB is V in minus VBE. V in is plus 5 volts. This is 0.7 volts. Then VRB is plus 4.3 volts. Okay. Then we can find RB. RB is VRB divided by IB. VRB is 4.3 volts. IB is 0.2 milliamperes. Then this will be 43 divided by 2. This is 21.5 kilo ohms. Okay. But we know that we have to maintain this relationship. This IC should be less than beta IB, otherwise transistor is not in saturated region. Then we have to increase IB little bit. Then when you have 21.5 K RB, then your IB will be how much? 0.2. When RB is 21.5 K, then IB will be 0.2 milliamperes. But here we can take RB as 20K. We can reduce RB a bit. Then when you reduce RB, IB will be increased. Then when IB will be increased, this relationship is not valid. Okay, here we are pushing the transistor into saturated region. Then only you can say VC is 0 volts. Okay. In practical cases, we can select this RB as 20K. Then that's what we have found. Then we have to calculate what is that? The other one we have to find this R1. How can we find R1? Without coming to the base side, still that we can find R1 also, because that across this R1 and here to here, VC is 0 volts. And you can write this equation plus VCC equals to V LED VR1 plus VCE. This is 12 volts. VLED is 2.2 volts. VR1 we don't know. Sorry, we know. We can find VR1, and this is VCE is 0 volts. Then VR1, how much it? It's 9.8 volts. And IC is how much? 20 milliamperes. Then we can find R1. Then we can find R1. R1 is VR1 divided by IC. It's 9.8 volts. This is 20 milliampere. And this is 0.49 kilo ohms. Okay. Then practically we don't have 0.49 kilo ohms. That the meaning is this is 490 ohms. R1. Then either you can select resistor ranges 470 or if we take 5% resistor, It will be wait. Four 4.3, 4.7, 5.1. We can take this one. 470 ohm resistor O, 510 ohm resistor. Practically, okay. But in your case, in that examination, that if you receive this answer, you can stay with this answer. But I am saying that practically you cannot find this one in the market. Because of that, you have to select either one of these. And if you select 470 ohm resistor there, then your LED light intensity will be a little bit increased. But 510, it will be a little less that one. But 510 is enough. Here. Okay, this is how we can use this circuit to turn on these LEDs. Okay, I'll give you a small example. If you're okay with this, anything you didn't understand? Okay, then if you're okay with this one, can I give you a small exercise? Then you have transistor here. Zero volts plus VCC. This is plus 18 volts. But Diniti, that it's not V in that according to the different V in values. But here we have taken V in as 5 volts and 0 volts. When you give 0 volts, transistor will be turned off. When you give 5 volts, then transistor will be turned on in saturate mode. But to push this transistor into saturate mode, what did we do? Here that when we use this beta to calculate RB, it is 21.5 K. But we know that to push the transistor towards the saturate mode, we have to give little bit more IB. Okay. When you give little bit more IB means we are giving VB is as 0.7 volts. Then maintaining 0.7 volts here and sending IB little bit more, then we are having the relationship with this. IC is less than beta IB. So beta is fixed. If you increase little bit IB, then this relationship will be there. Then based on that, we have pushed this transistor into saturate mode when V in is 5 volts. But still you can find that you can have the different voltage at if you want to use 6 volts there, if you want to use 9 volts there, for this if you want to turn on your transistor at 9 volts, what you have to do is that you have to put, instead of this 5 volts, you can put 9 volts here. Here you can put 9 volts. Then based on that, you can calculate RB. Then RB value may be different. Okay. Then for different voltage values, different RB values are there. But here I have taken to turn on the transistor, to turn on, it should be 5 volts, V in, and to turn off, we are giving 0 volts. That's what 2 voltages I have selected. But if you want that, you can select different voltages to this on and off voltages. Okay, this is switched off voltage. Here, switch on voltage. To switch on, we are designing this one. We want to turn on the transistor at 5 volts. Because of that, we calculate all other parameters accordingly. But if you want to have 9 volts to turn on the transistor, even though that if you want that to have 12 volts to turn on transistor, you can do that one also. It doesn't matter. But what is what is necessary? Only the necessary requirement is across this junction. Across this junction, you have to maintain this. It should be 0.7 volts. That's what we have to do. Is it clear? Okay. But here in this case, shall we try to do different thing here? Sorry. Here, assuming allowing beta of this transistor is 250 and LED to turn on LED, VLED, we have to give 3 volts and ILED, LED current is 40 milliampere. Taking these parameters, okay, and to turn on, you are using Vin as 9 volts and 0 volts to turn on and off. Here, this is turn on voltage, this is off voltage. And by taking these things, okay, we have to find IC, RL, IB, and RB. You can find these things also. Okay. RL, VRL. I think in the meantime that you will find these things also. VRB. Okay, here we can mark the currents here, and each LED is having 3 volts, and this current is 40 milliampere. Then across these two LEDs, we have then 6 volts drop. Okay, then 40 into 4, this IC current is 40 milliampere coming from each LED. Then we have to multiply that, and this is 160 milliamperes. Okay. The next one we have to find is from each LED. We have this 40 milliampere current coming through it, but across one LED we have 6 volts drop. Across two LEDs we have 6 volts drop. So 3 volts, 3 plus 3, 6. Okay. Then when we put this one into saturate mode, this VCE, we can take it as 0 volts. Then across RL, we can find voltage. RL is plus VCC minus 6 volts, then VRL is plus 12 volts. That is one of the answer we need. Then if you know VRL, then we can calculate RL. RL is VRL divided by IC. Here we have plus 12 volts. IC is 160 milliampere. Then RL is 12 divided by 160 milliampere. Then this is 75 ohms. Okay. Third one, if you want to find IB. Third one, you know that beta is 250. We have this IC, then IB we can find IC divided by beta. IC is 160 milliamperes. This one divided by beta. And 60 divided by 250. This is 0.64 milliamperes for 640 microamperes. Then we can find RB. To find RB, we have to take this VBE. This VB should be 0.7 volts, otherwise we cannot drive this one into saturate mode. When VB is 0.7 volts, and this IB, we know it, then we have to find VRB. VRB is here, VN we have to consider as 9 volts. This one is 9 volts, then 9 volts minus 0.7 is 8.3. VRB is V in minus VBE. Then this is 9 volts minus 0.7 volts. This is 8.3 volts. But you know IB. Then RB is VRB divided by AB. VRB is 8.3 volts. And this is 0.64 milliamperes. 3 divided by this is 12.96 kilo ohm. We can take it as 13 kilo. Okay. What is next? RB from VRL and VRB. VRL we know 6 volts. VRB 8.3. VRB 8.3. VRL 12 volts. Okay. One question asked in the exam, do we get the picture of the circuit or not? Yes, we have circuit diagrams. Actually, then where that we have some kind of calculation and coming to this 13 kilo ohm. But actually, what we want to do is that we want to push this transistor into saturate mode. What is the requirement for that one? We want to push this VB to 0.7 volts. When VB is 0.7 volts, we know that transistor is in saturate mode. Then we have to make sure that VB is 0.7 volts. To do that, what we have to do? When you calculate this according to beta value, when you take beta value and accordingly you can calculate IB value. When you calculate IB value across the RB, you have voltage drop. Okay. Then when we have this voltage drop, it will be balanced. Here we have 0.7 volts, but here we have VRB. Some value may be here. But with that, you have balanced voltage. but slightly, if VRB is little bit increased, then transistor will come to the linear region, active region. To make sure that transistor is VB is being maintained at 0.7 volts or even little bit more, what we have to do, we have to reduce this RB. Then when you reduce this RB, across RB, the current, this IB current is there. Then across RB, the voltage is little bit less. When you have the little bit less voltage across RB, then definitely the balance voltage will be appeared across the VB, across the base to emitter junction. Then it will be 0.7 volts or maybe going towards more than, little bit more than that. Then it will make sure that transistor is in active region, sorry, saturated region. Because of that, all the time when we calculate this RB, what we want to do to make sure that RB, the transistor is in saturated region, we have to reduce RB little bit. 12.96, that is the one. In practical, that we don't have exact 12.9 resistor, but we have 12 ohm resistor. The next one is 13 ohms. And we have 12 ohms and 13 ohms. Then here we have 12K or 13K we have to select. We have 12.96, then we can select 12K. All the time, select the little bit lower one. Next one, in the lower side. The resistor table, actually, that is not necessary to remember by all these things by heart. Anyway, I found this one from the web. These are the resistor preferred values. Okay, wait. It's shall we find the different one? A good one. Yes, this is good. This is good. Standard resistor values. Okay, but actually, we want to know about this row, this column. When you have one, it's 10, 100, 1K, 10K, 100K. This part is okay. Then when you have 3.3, 3.3, you have 33, then 3.3K, 33K, then 3 here also. One thing to write 33 and sorry 3.3 ohms. When you have this 3.3 ohms resistor, next one is 33 ohms. Then next one is 333 ohms. Then 3.3K. Then 33K. 330K. Okay, then next one 3.3 mega. Beyond this 10 mega, these carbon resistors are not available. Then from this 3.3, you have 1, 2, 3, 4, 5, 6, 7. 7 values. And from that, you can see that here we have 12, 13. Then 12K, 13K, this one. You have this 1.2, 1.3. Yeah, according to this table that you know that here, we have to select this one. Because our answer is 12.96. We have to make sure that transistor is in the saturate region. Then we have to select less one. Less than 12.96. The selection should be 12K or 13K. Less as is this one. And it should be 12K. Okay, here we have logic gate, digital logic gate. Okay, logic gates are working with plus 5 volts. That is a supply 5 volts and 0 volts. Then you know that logic level is 5 volts and 0 volts. When logic 1 is there, it will be 5 volts. When logic 0 is there, it's 0. Then here we have RB resistor, and this bulb is 6 volts bulb. Okay, with this transistor beta, it will be 150. Okay, then bulb is 6 volts, and wattage. Mm, 1.5. Okay, then here we have 6 volts, 0.5 watt bulb. Okay. Now we have these things. Then you have to find IC, IB, RB. Okay, how can we find this one? Then here we have included a bulb. Then and it will be driven by a logic gate. What are the things you should know here? What is V in? V in is 0 volts and plus 5 volts. This is logic 0 and this is logic 1. When the gate is giving logic 1 output, voltage will be 5 volts. When it is logic 0, voltage will be 0 volts. Then these are the two driven voltages, and then based on that we have to do the calculations. Okay. The other thing from the bulbs, it's mentioned that bulb is 6 volt, 6 volts, 0.5 volt. Then we have to find the current through bulb. Okay. Then to find IC, then it's 0.5 watt divided by 6 volts. Then you can find IC. Then it is 83 milliamperes. Okay. And you know that here, when we take this one, when we drive this one into saturation mode, this one is VC is 0 volts. Then the total voltage will be appeared across the bulb. Then bulb can give its full strength because the working voltage has been received. And now we know IC, then we can calculate IB, beta 150. Then IB, we can calculate IB is IC divided by beta. IC is 83 milliampere, beta is 150. Yes, 150. Then IB will be 53 divided by 150. Then it's 0.55 milliampere. So 550. Okay, we have another microamp. Then we can find RB. RB, then we have to find VB divided by IB. VB is 4.3 volts. This is 4.3. Why? Across this one we have 0.7 volts. then IB is 0.553 milliampere. To consider the resistor values nearest table, it is 7.5, 6.8, 7.5. We can take this one as 7.5. Okay. But this is the actual theoretical answer. This is correct, but according to the practical table, the practical available resistor values, this is the practical value we can take. And this should be theoretical value, and one we select should be less than this one. Okay, the couple of questions came from previous one also. I'll answer that one first. Here, voltage drop of LEDs as 6 volts because I have given here VLED. LED working voltage of LED is 3 volts. Here we have 2 LEDs. Then altogether it should be 6 volts. Okay. Then can't we take it as 7K ohm? This one. Actually, it doesn't matter. The 7.7 is the theoretical answer, but we have 7.5K ohm resistance. Okay. But to be in the safe side, that you can take 7 ohm resistor also, but shall we take the table? The table, we don't have 7K resistor. Then it should be 6.8K. Okay, the examination, I think still I have not decided whether this to give this table or not. If the table is there in the examination, you can refer the table and select the nearest resistor. And if the table is not there, you can have the theoretical one, calculated one there, that is enough. Okay, anything, any question? Okay, here that actually we have turned on small devices. Here we have used LEDs. The previous one also we turn on LED. And after that, we have turned on a torch bulb, something like that, a little bit the high voltage device. But if you want to handle another high voltage device, and having much more larger currents, but the solution, the circuit is same. The same circuit you can use. This is the transistor switch circuit. But here we can have a different arrangement. We have transistor, and this is our power line, 0 volts one, and this is our positive voltage one, VCC, and this is the current limiting RP resistor. This is V in. Okay, here you can put a relay. Okay, relay is a device having mechanical contacts inside, and this is a DC coil. It's working as a magnet. Then here you have a switch. Like this. You can consider this as switch. Then when the relay is turned on, this contact will be coming down. When the relay is in normal state, if the relay is off, then this contact will be there. Then we say this is normally closed contact, this is normally open contact, and this is common contact. Close. This is normally open. And this one is common contact. Even here that using this relay, you can use 230 volt bulb also if you want. But for the protection of this diode, this transistor, we are putting this diode in the reverse mode direction. We say this is flywheel diode. It's a protection diode here. With this protection diode, transistor will not be damaged. We say this is flywheel diode, or maybe actually this is a protection diode. If the calculation is same for this one, we have to find this RB and the suitable transistor for this one. In your case, for the examination, and all these values will be given, then you have to calculate the relevant values only. But I'm not going to discuss much more about these relay applications. Then you will have some kind of confusion, because sometimes that most of you may be new to this section. Then you will have a lot more things to remember. Because of that, I think this is enough that if you are okay with this one and this LED circuit, this circuit, and how to turn on this one, like that, that is enough. Anything, any question? What's the date your exam starts?
25th, sir.
26th,
5th.
25, right? 25.
Yeah, 25. Sir.
Yeah. Then, okay, that is Saturday, no?
Yes. Sir.
Yes, I'll upload these videos. Most of the time, that weekday batch that they have to refer these videos. But if it is necessary that I don't know that possibility, but it is not legal to have a additional class that during this 2 weeks time. But anyway, that I don't know that where do you have this paper? Have you received the timetable?
Yes, sir. The exam will conduct at FGS, Columbia University.
No, it's okay, but I'm asking the date of this paper.
This paper, sir, give me a minute, sir. I will check and